Welcome back to Bite-Sized Breakthroughs. I'm Alex Askwell. Today we're diving deep into a fascinating new paper, the DeepSeek-V3 technical report. We've got two experts with us, Dr. Paige Turner, the lead researcher behind DeepSeek-V3, and Professor Weed Spectrum, an authority in the broader field of large language models. Welcome to both of you.
Thanks, Alex. Happy to be here. Pleasure to be on the show.
Dr. Turner, let's start with the big picture. For our listeners who might not be completely immersed in the world of large language models, can you give us some context on where DeepSeek-V3 fits in the current landscape?
Absolutely, Alex. The field of large language models, or LLMs, has seen incredible progress, with models like those from Anthropic, Google, and OpenAI at the forefront. But there's also been a strong movement towards open source models, which aim to bring these capabilities to the wider community. DeepSeek V3 is our contribution to this. We're aiming to not only compete with leading closed source models, but also push the boundaries in terms of cost effectiveness and efficiency. Models like the DeepSeek series, Llama, Qwen, and Mistral are all examples of open source efforts trying to narrow that gap.
So it's a crowded space, but with the goal of democratization. Professor Spectrum, how significant is this drive towards open source models in the LLM field?
It's tremendously significant, Alex. The push towards open source LLMs is about more than just making these models available. It's about fostering transparency, collaboration, and innovation. It's essential for leveling the playing field, allowing researchers and developers worldwide to access and build upon these technologies without the constraints of proprietary licenses. It also helps with transparency and accountability in an area that is often a black box.
That makes perfect sense. Now, Dr. Turner, let's get into the specifics. What are the key contributions of DeepSeek V3? What makes it stand out from its predecessors and competitors?
Okay, there are a few main contributions. First, we've developed an auxiliary loss-free load balancing strategy for our mixture of experts MOE architecture, which we call DeepSeek MOE. MOE models are like having a team of specialists, where different parts of the model are activated depending on the input. However, it's tricky to keep the workload balanced across those experts. Traditional methods have used auxiliary loss functions to help with this, but these can actually hurt performance. We've designed a system which is entirely free of that loss function and only relies on dynamic bias adjustments. Secondly, we've implemented a multi-token prediction (MTP) training objective. Instead of just predicting the next word, our model attempts to predict multiple future words sequentially. This densifies training signals and can lead to faster inference, as we can use this for speculative decoding. Thirdly, we've built an FP8 mixed precision training framework and, for the first time, validated this approach on an extremely large-scale model like DeepSeek V3. FP8 stands for 8-bit floating point, and it allows us to dramatically speed up training and reduce memory usage, and it's something that traditionally has been very hard to achieve. Then, our optimized DualPipe algorithm for pipeline parallelism, coupled with very efficient cross-node communication kernels, has helped achieve near-full computation communication overlap. And lastly, we've shown that the techniques we use to perform knowledge distillation from the DeepSeek R1 series of models has been very effective.
That's a lot to unpack. Let's start with the MOE architecture and this auxiliary loss-free load balancing. Could you explain the concept of mixture of experts, or MOE, a bit further for our audience?
Certainly. In traditional neural networks, every part of the network is involved in processing every input. In contrast, an MOE model is essentially a collection of separate neural networks, or experts, and for each input, a routing mechanism selects only a few of these experts to process it. This allows for a significant increase in the total number of parameters, which can enhance capacity without a proportional increase in computation for each individual input. DeepSeek MOE is our specific version of MemoE, which uses finer-grained experts and also isolates some experts as shared. But let's focus on the dynamic load balancing you asked about. Think of it like a relay race where each team member, our experts, needs to carry their load, and you don't want one person doing all the work. In our model, we use a sigmoid function to compute an affinity score, indicating how well suited the current input is for each of the experts. The core innovation is that Instead of relying on a separate auxiliary loss function to penalize experts that are overloaded or underutilized, we dynamically adjust a bias term added to the affinity score used for routing. If an expert is consistently overloaded during training, we reduce its bias, and similarly, increase the bias for underutilized experts, making it more or less attractive to the routing mechanism. Crucially, this bias term isn't used when we compute the contribution of an expert, only when we decide which experts to send the input to. So it's used for routing and routing only, and doesn't contribute to the model's performance directly, but ensures effective load balancing.
And the critical part is that this approach avoids a common issue where forcing load balance with an auxiliary loss function actually hurts overall performance, correct?
Precisely, Alex. Previous research showed that while auxiliary loss functions are effective in achieving load balance, they also degrade model performance because there is a tension between performance and balance. Our auxiliary loss-free approach provides the best of both worlds by achieving a better trade-off between these competing objectives.
And Professor Spectrum, what's your view on this auxiliary loss-free approach in the context of other MOE models? Is this a common problem area?
Absolutely. Load balancing in MOE models has been a persistent challenge, and the use of auxiliary loss functions, while common, has always been somewhat of a workaround, with an undesirable impact on performance, as has been indicated in previous research. What Dr. Turner's team has achieved by removing this loss function and dynamically adapting bias during routing is a significant step forward. This approach not only improves load balancing, but also minimizes its negative side effects. It's a very elegant solution.
Okay, let's move on to the multi-token prediction, or MTP training objective. How does that work?
So typically in LLM training, the model is trained to predict only the next word or token in a sequence. With our MTP objective, at each position of the input sequence, we also predict multiple future tokens. The key is that we're not predicting them in parallel. Each is predicted sequentially, and each prediction is conditioned on the prior predictions. So if we're doing 2-token MTP for each input word, we're not only predicting the immediate next word, but also, using the hidden representations of that, we're predicting the word after that using a separate prediction head. This densifies training signals as there's more information available during the training phase, because for every input token, we are training on multiple target tokens, and we see evidence that it also helps the model plan ahead in terms of the representations it's creating for the prediction. A crucial point is that during inference, we can discard this MTP module and just use the model as normal. The MTP objective is primarily for improving training. However, these same MTP modules can also be used for what we call speculative decoding, where you predict some future tokens using a fast draft network that is less expensive and confirm it with the main network. This reduces the latency during the generation of long text.
So it's both for better training and faster inference, a 2-for-1. Professor Spectrum, what are your thoughts on this approach compared to more traditional next token prediction methods?
Well, the idea of using a multi-token prediction target isn't entirely new, but Dr. Turner's team's implementation, which keeps the full causal chain, is a very clever and significant departure from previous methods, which tried to make such predictions in parallel. This approach better reflects how language is constructed in a temporal way, one word at a time, and also lends itself naturally to speculative decoding, where a draft network, in this case the MTP module, can make predictions that are then confirmed by the primary network, speeding up inference. It's a really smart approach that could have widespread applicability.
Let's talk about the FP8 mixed precision training. This is probably something most of our listeners haven't come across. Could you explain what FP8 is and why it's important in the context of training these massive models?
Absolutely, Alex. Standard training of LLMs is done using what we call FP32, which is 32-bit floating point numbers. These provide a very high level of precision, but at the cost of requiring a lot of memory and computational resources. FP8, on the other hand, uses only 8 bits to represent the same type of information, significantly reducing memory and allowing for faster computations. The challenge, of course, is how to achieve the same level of model accuracy while using the less precise format. That's why mixed precision training is essential. In our case, we're not running everything in FP8, only the most computationally demanding operations, like the matrix multiplications in our linear layers, which are also known as general matrix multiplications, or GEMs. And while these are performed using FP8, we keep other operations, which are sensitive to precision, such as embedding, layer normalization, and attention, in their original data formats. We also introduce a technique to increase the precision of the matrix multiplications by promoting from tensor cores to CUDA cores at intervals of 128 elements and performing high-precision accumulation in FP32. Further, in order to extend the limited dynamic range of FP8, we introduce our fine-grained quantization strategy, which involves tile-wise 1 by 128 scaling for activations and block-wise 128 by 128 scaling for weights. This allows us to mitigate errors that come from feature outliers and generally helps us to maintain training stability.
Professor Spectrum, what is the general trend in the field with regards to these low-precision methods?
Low-precision training is a critical area of research. As models get bigger and bigger, the cost of training them using traditional 32-bit or even 16-bit floating point becomes prohibitive. There's now a general consensus that the way forward is to move toward these lower precision formats like FP8. Dr. Turner's team's work here is a major contribution, as it shows that this is a viable pathway forward even for the most demanding models, provided you have appropriate strategies to combat the decreased precision.
Let's move to the training infrastructure you used for DeepSeek-V3. You mentioned the DualPipe algorithm. Can you explain what that is and how it contributes to the model's efficiency?
Certainly, Alex. Training models like DeepSeek-V3, which involves an enormous amount of computation, requires very efficient distributed training. Pipeline parallelism, PP, is a common method where different layers of the model are deployed on different GPUs and compute is passed through each stage. A basic version is called 1F1B, short for one forward, one backward pass, which alternates between forward and backward computation on different stages. This results in pipeline bubbles, meaning that some GPUs are idle while other GPUs are working. While other approaches have tried to minimize this issue, like zero bubble, the challenge is that cross-node communication for MOE training results in inefficient computation-to-communication ratios. Our DualPipe algorithm is designed to address this. It overlaps the forward and backward computation phases and significantly reduces pipeline bubbles by using bidirectional scheduling of microbatches from both ends of the pipeline. The key is that we divide each chunk into components. For example, the attention operation, the all-to-all dispatch, the MLP, and the all-to-all combine, and we rearrange these in a specific order which allows us to overlap communication with other operations and to adjust the number of streaming multiprocessors, or SMs, used for communication dynamically. This ensures that we're minimizing idle time and maximizing utilization of hardware, even when there is heavy communication.
And Professor Spectrum, is it common to have this level of optimization in the communication layers?
It's becoming increasingly necessary. As model sizes increase, the bottleneck is often communication, not computation. And that's particularly true for the MOE architecture, which can require heavy communication across multiple nodes when an input is sent to multiple experts. The DualPipe scheduling that Dr. Turner's team has developed is extremely sophisticated, and it really demonstrates that there are more ways to push efficiency in large models than just scaling up hardware. It represents a critical advance in distributed training and could be crucial for future work in this area. The fact that they have optimized their cross-node communication to leverage different bandwidths of the InfiniBand and NVLink hardware further shows their attention to detail here.
All right, let's talk about the pre-training data you used. I understand you trained on 14.8 trillion tokens. Can you tell us about the data composition, its sources, and any specific filtering or processing techniques you used?
Yes, Alex. Our pre-training corpus consists of a vast amount of high-quality and diverse text data. We've made a deliberate effort to enhance the ratio of mathematical and programming samples while increasing multilingual coverage beyond English and Chinese. We have various sources, both private and public data sets that we can't go into detail on, but it's important that data processing pipeline is rigorous and minimizes redundancies while maintaining the diversity. We use document packing to keep the integrity of the documents and the fill in the middle or FIM strategy that has been used in previous models such as DeepSeek-V3. This involves using a special format to structure data where a document is split into prefix, suffix, and middle parts, and the model has to predict the middle based on the prefix and suffix. We also added special tokens to the tokenizer that combine punctuation and line breaks. This improves efficiency in many cases, but can introduce token boundary bias when processing multi-line prompts that do not end in a line break. So we mitigated this during training by randomly splitting these combined tokens and exposing the model to different cases.
Professor Spectrum, the scale of training data has a big impact on performance, but there are also increasing concerns about quality and bias. What are your thoughts on these aspects?
The sheer scale of training data is certainly a key ingredient for performance in these models, but it is definitely a balancing act. You need both the scale and quality, and diverse sources is also key to minimize biases. Dr. Turner's team's attention to not only the quantity, but also the composition and processing, and their rigorous approach to filtering and mitigating token boundary bias is crucial for ensuring a robust and reliable model. It's also important to note that the ethical considerations of using potentially biased or harmful training data is an ongoing challenge in the field and an area of continued discussion.
You also mentioned context length extension and that you are able to handle 128K token input. Can you explain that process?
Yes, Alex. Our pre-training is done using a context length of 4K tokens, which is quite small compared to the 128K we can handle in the model. To enable DeepSeek-V3 to handle longer context, we use a method called YARN to modify the rotary positional encoding, or ROPE, which is the method used to inject information about the token position into the embedding. We then conduct 2 additional training phases, increasing the sequence length first to 32K, then to 128K. This extension process is critical for long context tasks, and we have good results on benchmarks like needle in a haystack, where the model performs consistently across the 128K token range.
Let's delve deeper into the post-training process. You mentioned supervised fine-tuning, or SFT, and reinforcement learning, or RL, with knowledge distillation from DeepSeek R1. Can you walk us through those steps?
Certainly. The pre-training gives us a base model that can predict text, but has not been aligned to human preferences and desired behavior. We do SFT and RL to do that. For SFT, we curated a dataset of 1.5 million instances spanning different domains and using different strategies. Specifically, for the areas of reasoning, such as mathematics and coding, we leveraged the DeepSeek R1 models to generate data. That data showed strong accuracy, but had issues with length and style. Our training process involves using both original data and R1-generated data, some with and without system prompts, and the goal was to have our model produce responses that had the high accuracy of DeepSeek R1, while also being concise and clearly formatted. We achieve that by doing reinforcement learning using a combination of rule-based and a model-based reward model. For each instance, we sample several outputs and optimize based on the rewards of those outputs using Group Relative Policy Optimization, or GRPO. Finally, the knowledge distillation is the process of training the DeepSeek-V3 model on outputs from DeepSeek R1. Through this process, we are able to inject the reasoning capabilities from the R1 series of models into V3.
So essentially taking the best of DeepSeek R1 and combining it into DeepSeek-V3. Professor Spectrum, how does this distillation process compare with other post-training methods you are aware of?
It's a very clever approach because it combines the strengths of 2 different models in a very effective manner. DeepSeek R1 is good at complex reasoning, but may be too verbose. So DeepSeek-V3 leverages this by mimicking the high reasoning performance while retaining its short output style. Using the R1 outputs as training examples for SFT, combined with the feedback loop from the RL, makes this approach quite unique. I believe the method of leveraging powerful reasoning models for the post-training of LLMs is going to be a critical area of investigation going forward.
Now let's shift our focus to the experimental results. What benchmarks did you use to evaluate DeepSeek-V3, and how did it perform?
We used a very comprehensive suite of benchmarks to evaluate DeepSeek-V3, both in its base and chat versions. These included widely used benchmarks such as MMLU, a multi-subject multiple-choice test, and more challenging variations like MMLU Pro. We evaluated on the DROP benchmark for reading comprehension and the GPQA benchmark, which tests graduate-level knowledge. We also tested on factuality benchmarks like SimpleQA and the Chinese version, C-SimpleQA, as well as datasets for code generation like Human Eval Mol and Live Code Bench, and a number of math-related benchmarks such as GSM-8K, Math, MGSM, and CMath. On the English side, the chat version was evaluated on Arena Hard and Alpaca Eval, which uses LLMs as judges to evaluate open-ended generation. Overall, the base model outperformed existing open-source models and matched or surpassed leading closed-source models on many of the benchmarks, with particularly strong performance in coding and mathematics. As a few specific examples, on MLU we got a score of 88.5, 75.9 on MMLU Pro, and 59.1 on GPQA Diamond. In math, we got a score of 90.2 on Math 500, and in coding, we scored 40.5 on Live Code Bench COT. As for training, the model was trained on 14.8T tokens, required only 2.788 H800 GPU hours for the complete training, and achieved extremely stable training without rollbacks.
And Professor Spectrum, how do these scores compare with the current state of the art?
The results are remarkable, Alex. The scores on benchmarks like MMLU and GPQA place DeepSeek-V3 in the same league as leading closed-source models. The performance on math and coding benchmarks is particularly impressive, outperforming all other open-source models and even some closed-source in those areas. And crucially, these results have been achieved at a much lower training cost. This shows how effective the combination of techniques they've implemented are.
Let's talk about limitations. What are some areas where DeepSeek-V3 still has room for improvement, or where you've identified constraints?
While we're very proud of the results, we also recognize some limitations. First, the model's deployment footprint is relatively large, requiring a substantial amount of GPUs for efficient inference. This could be a hurdle for smaller teams. While our MTP approach improves decoding speed, it is an area we will continue to improve, as well as the memory footprint of the model. Furthermore, our focus on training in Chinese means it is not as good in factual English questions as other closed-source models. We also recognize the potential for the token boundary bias from our tokenizer to affect multi-line prompts, even though we address this during training. Finally, our inference load balancing could be made more dynamic by adjusting the redundancy of expert deployment based on observed loads during inference.
And what future directions are you considering as next steps for the research and development?
We have several important directions we're going to be exploring. We'll continue to refine our model architecture to improve both training and inference efficiency, aiming for better support for longer context lengths, as well as exploring alternatives to the traditional transformer architecture. We're also focused on improving the quantity and quality of training data, expanding it to encompass new domains and new training signals. Further focus on the reasoning capabilities of the model, extending the chain of reasoning, and evaluating the model using comprehensive multidimensional benchmarks rather than a fixed set of tasks. Finally, we'll be exploring new methods for improving the deployment size to make this more accessible for smaller teams and more advanced techniques to support scalable self-improvement via better reward models.
Professor Spectrum, what are your thoughts on these limitations and future directions?
It's a very sensible roadmap. The limitations identified are typical for models of this scale, and the directions Dr. Turner has described address crucial challenges in the field, such as accessibility, scalability, and safety. It's essential to keep pushing on these limitations, particularly in areas like model deployment footprint, and exploring alternative architectures that could move beyond some of the constraints of transformers. It's exciting to see how they approach the next steps.
Before we wrap, let's consider the broader impact of this work. What are the potential applications, and how might DeepSeek-V3 contribute to various fields?
The potential applications for DeepSeek-V3 are incredibly diverse. Its strong coding capabilities can drive advancements in software development with the creation of tools that can assist developers and help debug programs. Its advancements in mathematical reasoning could be applied to scientific research and automation of scientific tasks. Its reasoning skills and performance on MMLU Pro could create new possibilities for education and automated tutoring systems. Furthermore, with its multilingual capabilities, it can be deployed for automated translation systems or multilingual content generation. Its abilities for open-ended generation can be applied to assist in creative writing and content creation. And the fact that the model can be used as a powerful reward model will be valuable in the creation of more self-improving AI systems. The availability of this powerful open-source model at a relatively low training cost could greatly democratize access to powerful AI tools, enabling smaller teams to participate and innovate in this space.
Professor Spectrum, what are your thoughts on these potential applications and the broader impact?
I agree completely with Dr. Turner. The sheer breadth of potential applications, from coding and mathematics to creative content and education, demonstrates that this is a model with widespread impact across diverse fields. The open source nature is crucial because it allows other researchers, developers, and companies to explore these applications. The advancements made through techniques like FP8, DualPipe, the MTP objective, and the auxiliary loss free load balancing method contribute not just to the model itself, but also the broader research and development community and the field as a whole. And finally, it can be said that the increased access that this project enables also brings a greater need for responsible development and ethical considerations, which is a growing area of discussion in the AI field.
That's a fantastic overview, and I think we've really covered a lot today. So in summary, DeepSeek V3 has made significant progress in a number of ways. The unique auxiliary loss-free load balancing for MOE models is an important step forward, with more efficient computation and the MTP approach, which both densifies training and accelerates inference. FP8 training shows it can be used reliably and can allow for more accessible training. The extensive evaluation demonstrates performance on par with leading closed-source models, and it has become a leader in the open-source community for coding and math tasks, while also proving an efficient method for knowledge distillation. It has provided a novel approach for distributed training. Thanks for both of you for helping make this paper accessible to our listeners and for clarifying these critical points.
Thank you, Alex. It was great to be here.
My pleasure.